Hi everybody. So we're starting part 3 of this EICO ST70 video down in the workshop. Down here I got the heater on and thought I'd show you a little thing that I found here online, and it's actually been really pretty cool. If you look here, I have a little device you can see here called you can see here, disc cutter. Okay, see there, disc cutter. And what this thing does is it's basically some punches, some drift punches. And if you look here, you take a piece of thin aluminum or sheet metal and you place it inside here. Okay, and I can't do this with one hand, so I'm just going to have to show you the process. And basically you place it in here, you put the pin in, and then time to play a big game of whack-a-mole. So I use a piece of wood. I don't want to flare out the metal on this. I basically pound it through, and basically makes these little discs. Now you might ask me, why am I doing this? Well, if you recall from the ST70 and a lot of the old vintage radios and stereos out there, a lot of the plastic knobs have these little inserts, and they have a tendency to fall out and get lost. And I was wondering to myself, you know, there's some people online that sell them, but they're kind of pricey, and most of them are just not available. And being that this is older vintage gear, most of the time everything is done in SAE, you know, so you can buy these in metric as well, but all the vintage gear that I've worked on has used all SAE. Now this is a little bit fancier. For about $35 you can go online and you can type like on eBay or Amazon or someplace, you can type in disc cutter or jewelry disc cutter, and basically you get this punch block right here, as you can see, and you get the punches. Now the less expensive sets just comes with the die or the punch block and just one set of flat punches. Now you can also get a convex and concave set like I did here, and that allows you to, as you punch them through, make an actual, like a conical shape. I'll punch one of those out for you here next. But let me see if I can kind of go through the process with you here without causing too much trouble with the camera. And I'll see if I can get a view here where you can actually see me use this thing. Let's see what we can get in here, if we can get this in the shot. Okay, right like that. So basically, take this, put it in the die, like so. Put the punch in there, and then just pop it through, just like that. And as you can see, pops this perfect little disc out. Okay, so then what you can do, hope you saw that, then what you can do is you can actually polish this and put a shine onto it, or paint it, or whatever you want to do, and then glue these in. Now when I get back down to the bench, I'll show you how these fit perfectly inside the EICO knobs. And this is a 7/8 inch disc right here, and it fits perfectly, press fit right in there. And you can also go to like craft stores and so forth, and they sell really thin like copper sheet and brass sheet that's really nice, kind of a coppery gold color, so you can use that. There's all kinds of different options when you use these punches, and it's kind of a way that you can make your own custom inserts for your plastic knobs, especially the ones that are damaged or the pieces are missing or whatever. So let me punch out a couple others and I'll show you some of the results, and then we'll take them down to the shop, and from there we'll take a look and see how it looks. Alright, I'll be right back. Alright, so I just punched a whole bunch of these out, and here is the convex, concave, whatever you want to call it, the pointy ones. I think those would look kind of cool. And then here's the flat ones. And then I punched out a couple of the 3/4 inch smaller ones too. Don't know what I'm going to do with them yet, but anyways, we can do the same with you know, pieces of copper or brass sheeting. Any soft metal, I don't know that I would want to punch anything hard with it, but that's it. I did try to use my arbor press, and I can tell you that it's just a little bit too hard to push through the metal, even with this thin aluminum. And you can see this is like, what is this, 18 gauge aluminum? And probably that's a little thick. You could probably punch 20 gauge or 22 gauge a lot easier, but regardless, it did go through pretty easy. Couple of notes for using this. Do not beat on these with your hammer. The hardened hammer face will eventually cause these to mushroom out. They are chamfered a little bit on the edge, if you can see, but I don't know that I'd want to try that. I use just a piece of, block of wood to absorb the impact, and then I just use my brass drift pin here to push it through, because there's still friction as the punch moves its way through the aluminum. So expect to get some crud on your fingers, but really it's a pretty simple process. You just pound them through and you can make all these little inserts, and you can restore all of your old knobs, and change the little knob inserts. So I hope this was a helpful tip, and we'll go up to the bench now and we'll see how they fit in one of them. But I'm actually not done with the knobs. I want to try to clean them up a little bit better. I may try to use that method where you take the hydrogen peroxide and ultraviolet light, from the sun, and get the, put it in a plastic bag out in the sun, and hopefully it'll whiten the plastic and clean it up a little bit better. So I may do that, and if I do that, I really don't want these in there while I'm doing that. So I probably won't press these in until then, but we'll look at one and see how it fits anyways. Alright, so we will be back. I hope this was a helpful tip to you. Alright, we're back down here on the bench, and in front of you here I have one of these knobs. And you can see there's the single piece knob and the two-piece knob. Okay, so there's two different kinds of knobs that comes on these radios, but they have the same faces on the top. And if you notice, all the inserts were missing from these. They had all fallen out. You can kind of see in there where there used to be some glue holding it, but I just kind of show you. So here's one of the domed ones, pointy ones that I made, and you can see they fit right in there like that. And you can see when it's done, I don't have it pushed all the way down, but it will push right straight in if I push it. And then actually the press fit is so good, I doubt that I would even need to glue it. And you can see how that looks, nice and new. So I think this is a good solution for this, and I can't tell you how many knobs I've gone through over the years that had their little inserts missing. Some of them, like the Fisher knobs and everything, they have a fold over. So like they, instead of the knob going, or the top going inside, they go over. So like they're have a lip all the way around. And I'm not sure how good that would work for this, but in retrospect, you may not have the wraparound effect, but you could still punch those, and if they're the right diameter, you could epoxy them on, and even though they wouldn't have the wraparound effect, you still would have the top cap covered with that, which still would look pretty good. So anyways, with that in mind, I just thought you'd like to see that little tip. And what we're going to do here is, this still, I haven't started on this yet. And you're not going to probably see this part 3 video for a little while. So there's going to be like a time gap between this shot right here and then the next shot in part 3, because I actually, the owner of the Jackson Bell radio supposedly has gotten in all the tubes, and I want to get that finished for him. I want to get that, see if we can get it to tune in and work, and then once we complete that project, then we'll be right back on this, and I'll do all the capping and everything on this, and then get it posted up. So hang in there, and I guess we'll be back here. But through the magic of the camera, it'll be a split second, but in real time, we'll be back in a few days. All right, until then, we'll talk to you later. Okay, everybody. It's been about a week's worth of work here, just on and off between, when I have some free time between the business and the family and all the other million things going on. But here's where we are. As you can see, we made a ton of changes to this amp. So I'll try to go over them with you here as best I can. Now, first of all, the first thing I need to do is give credit where it's due. A lot of the research that went into choosing the components and the modifications, some of them I chose myself, but some of them I have to give credit to a man by the name of Stephen Lafferty, who's posted a document online of some of the work that he's done on one of these, and so I want to kind of give him credit for that, and I'll try to put a link to it on the website, or on this video. Okay, sorry about that. I had a little interruption there. Had some things I had to do. Anyways, where I left off, lots of changes in this, so I'll try to go over them with you. Let's start with the phono preamp first. Now these tubes here, this one here, and this one here, V1 and V2, are your phono preamp tubes. They're 12AX7s. And by and large, it's a pretty decent layout the way they did it. Let's see if I can get the schematic here for you and show you what we're doing. And I pretty much followed the instructions that I read on the on the little document. But pretty much there was only two changes. The first change was these capacitors that were in here, believe it or not, were actually ceramic discs. Now, any of you who work with audio kind of know that ceramic discs really are not a good choice for capacitor for being in the audio path of, especially of a good audio amplifier. There's a lot of reasons, and you can look that up online, some of the differences between different types of capacitors, but ceramic discs just aren't a good choice. So the first thing we did was two things. We went from a ceramic capacitor to a more to one of these Solon capacitors here, film capacitors, or polyester capacitors as they call them. And these are very high quality, and I used those in place of the ceramic discs. But what's more, I went from the 0.025 to a 0.1 microfarad. Now, why would you do a thing like that? Well, whenever you're using a capacitor as a coupling device, especially like in these, let's talk about in the context of tube amplifiers, whenever you're using a capacitor, as you see them all through here, as a coupling device, the first purpose of a coupling capacitor is to remove the DC component from the circuit. In other words, we don't want DC getting into the grids of our tubes, because that will offset the bias of the tube. You only want AC to be on that grid, so as far as signal is concerned. So you put that capacitor in there, which will block the presence of DC but it will pass AC right through it. Now the value of the capacitor, how much capacitance it has, affects a bunch of different things in a bunch of different ways. So suffice it to say, and I'm going to try to keep it simple, the value of the capacitor kind of has a, well, doesn't kind of, it definitely has an effect on what frequencies pass through that capacitor and how those frequencies roll off. In other words, by putting a bigger capacitor, you can allow a lower frequency to pass through the capacitor with respect to how much current the signal on the other, or the grid on the other side requires to be able to do its job, if that makes any sense to you. So the idea is to put a small enough capacitor to block out any subsonic sound and any DC, but have it to be a large enough capacitance to allow the bass notes to come through. And it's different for each type of circuit that you're designing. So not every tube circuit is always going to have the same value of capacitor. And you do have a choice. You can play with those numbers a little bit. So basically, a known issue with these EICO amps is that in the phono section, they're a little bit weak in the bass notes, okay, in the low end of the audible frequency spectrum. So to correct for that, we raise the capacitance from a 0.025 up to a 0.1 microfarad. So these new caps here, okay, so where we used to have these ceramic discs, if you go back and look at the earlier videos like this, we now have these ones which are 0.1. Now what that's going to do is that's going to allow more energy through that capacitor, and it's going to allow especially the lower frequencies to come through a little stronger and to roll off a little bit later. So what that means is we're going to get a better bass response. But what that's also going to do is it's going to throw off what we call the RIAA equalization of that circuit. I know I'm talking a lot about a little bit here, but it's kind of important. Whenever you deal with a phonograph or a record player, you have a cartridge, and it's either a magnetic or ceramic. In this case, it's magnetic. In other words, a low output phono cartridge. So the needle, the stylus, vibrates on the record, and that vibration moves either a little magnet or a little coil inside the cartridge, and that cartridge produces a very, very, very small signal that is representative of the sound that's been imprinted onto the record. And the problem is a cartridge is not linear. In other words, it doesn't have a flat frequency response to those grooves in the record. So, my kids are upstairs banging around. Anyway, so basically it's not equalized. So if you just amplify the signal as it comes out of a phono cartridge, it's not going to be a balanced sound. It's not going to reproduce the sound accurately to the way it was recorded. So what you'll find is things like the bass notes are going to be at a different volume level than the mid-range notes and then the treble notes. All the different frequencies are going to be out of balance from one another. So you have to rebalance that, and we call that equalization. Okay, and the RIAA, and that is an acronym, and it's slipping me what it means right now. Sorry about that. It's recording something or other. Anyway, they have created a standard of equalization that will equalize all of the frequencies to flatten them out in a phono preamp stage. Now, by changing the values of these components, we are playing around with that equalization. So we fix a problem and we create a new problem. So by changing this, we will get some more bass, but it's also going to offset the other frequencies, and we're still not going to be balanced. We have to do one more step. And that's where this comes in, okay? So if you notice, we put a 500K, and I can show you them here, one here and one here, 500,000 ohm potentiometer, okay? So essentially what we're doing is we're shunting that pot across this 68K feedback resistor. Okay, you see that? So what this resistor is doing, to my understanding, and again, I'm kind of just paraphrasing things that I've read, between these two cathodes, they're actually causing a little bit of feedback between, from this stage to this stage. And by adjusting this resistance in here, making it a little lower resistance, we actually are going to introduce a little bit of positive feedback into this tube through this resistor. Now, we know that positive feedback is typically a no-no in anything except for an oscillator, because an oscillator circuit is based on positive feedback. So if you have positive feedback in your feedback loop of your output section of your amplifier, it will horrifically oscillate and maybe even damage your tubes. But in this case, we're putting a tiny amount, just enough that at certain frequencies it'll balance it out. So basically what we're going to do is we're going to apply a higher frequency, let's say 1 kilohertz, and we're going to measure the output coming out of the tape out. Okay, so we're going to measure the output here, and then we're going to go and we're going to apply a low frequency like 25 or 30 or 35 hertz, and we're going to measure the level. Now, in order to do this, you have to have an audio signal generator that can output a consistent voltage at all different frequencies. And the whole idea is, if I put in a certain millivoltage of one frequency into this circuit and measure another, measure of certain voltage level out, I should be able to put the identical voltage level of a lower frequency in here and get an identical voltage level of that same frequency out. If they don't equal, frequency 1 versus frequency 2, then the gain is not flat through this. So what we're going to do is we're going to adjust this loop gain here until at both ends it balances out. Somewhere at some point we'll adjust this where it'll work, or it's supposed to work, and give you a level frequency response across the board. So that's what we're going to try to do. That's number one. Okay, very long-winded speech on the phono section. Now when you look at the rest of this, down in here when we get into the preamp and the driver section, any resistors that were out of tolerance or anything, I changed those, kept all the ones that were perfect and good, and we also changed some values of some things. The other thing I did was I put new pots in. The ones that were in there were working, but they were kind of noisy. They were carbon track potentiometers. These are actually wire wound, so they're a lot better for voltages. Those other ones are kind of a little better for signals, but you really don't want to put high voltages or anything on a carbon potentiometer. So I swapped these out with good ones. And we basically have several adjustments. You could see 1, 2, 3, 4. Okay, so you have 3 adjustments on each 1, 2, 3, 1, 2, 3 for each channel. Let's go over what those adjustments are and some of the changes we made. So the first thing is in your little preamp, and now we're talking the preamp of the line stage, not the phono preamp. We get out of the phono, and the next stage we get into here is the line stage preamp. The first thing we did was we added a 100K resistor, okay, into this grid. This was originally direct connected from the volume pot right into the grid, okay. Excuse me, I will be right back. Okay, sorry about that. So this tube was originally a 12DW7. Now what is a 12DW7? Well, by all intents and purposes, a 12DW7 looks just the same as a 12AX7. So you can see the two tubes here. They look very similar. This one's got a little bit shorter plates than this one. Here's a 12AX7. Here's a 12DW7. And really the main difference is this one has two different types of tubes in one, and this one has two of the same type of tube in one package. So these are 12AX7s are a relatively high gain triode tube. And this one has basically one section of, let's say, a 12AX7, a higher gain, and the other section it would be similar to a 12AU7, which is a medium gain tube. So you got two different elements with two different gain values. And the reason they did that was to save space. You can have one tube here, one package, take the place of two individual triode tubes that are different. Now, the problem with that was, by having two different gains, you're putting most of the work on one side more so than the other. The other thing that's happening is, by increasing the gain and everything on one side, it actually made these amps have a lot of hiss and a lot of hum at low volume. So when you turn these down the whole way, or if you're listening to a quiet passage of music, you very often would hear a lot of hiss. And I remember this on my cousin's amplifier, that although it sounded very good when it was fully active, when you got to a quiet passage or when the amplifier was not turned up real loud, you would hear that characteristic hiss. And this is going to try to address some of that. So the first thing we do is we put this 100K in series with the grid. Okay, and then we're going to change the gain of the amplifier, the biasing of it, by replacing the values of these resistors. Now this used to be like a 33K, and this was like a 1.8K. We changed them to a 100K resistor and a 2.2K resistor bypassed with a 100 microfarad capacitor. And we do the bypass to increase the gain and to increase the low end. So again, we're leveling out the bass, we're bringing it up. At the same time, we're removing this section, and now these are both 12AX7 high gain stages instead of a high and a medium. And this we're pretty much keeping the same, because this was the 12AX7 or the high gain section. This was the medium gain section. So now we're getting a little more gain out of this side, and we're kind of balancing things out. Okay, and we're kind of decoupling some of the noise from over here to over here by having this 100K. Now again, 100K resistor, that's a lot of resistance, but the grid of a tube is a kind of a unique thing. Is very, very sensitive to very, very, very small signals. So it doesn't take much in the line of current to drive the grid of a tube. All it cares about is voltage, and we know that if we're not drawing a lot of current through a resistor, it won't drop a lot of voltage across it. It depends on the impedance of what you're going into. The impedance of this grid is much higher than 100K. So this is not really dropping a lot of voltage, but it is limiting it somewhat. It's limiting the power into that grid and causing it to be a little bit quieter. So that's why we're doing this. Okay. We also changed this little feedback resistor from a 220K to a 1 meg. Okay. So all these things are in there for the purpose of reducing noise. Okay. And again, I'm trying to explain this as best as I have figured it out. And again, this is not my personal design. This is something that I've found and read, and read it very carefully and went over it, and it all makes sense to me. So we did all this, and then when we get over to the driver and output section, we made a couple of changes here. The first thing we did was we got rid of that center channel. They used to call those phantom channels in the old days, in the 50s and 60s. And the idea was you would have your right and left, and then you would have your center channel, kind of like a poor man's surround in a way, but to give you a more full sound stage. But we don't do that anymore, and I never use it, so I removed it out of there. The other thing is they originally had your feedback coming out of the 16 ohm tap, and they had the 4 ohm tap set to ground, and the common was floating. It's a really, really weird combination. So this goes to more of a traditional design. We've now moved our tap. If you look over here, lots of work here. We basically took our ground leads and we took the common lead of our output transformer and we put them directly to ground. Okay, so that's the first thing. This terminal here is soldered directly to the chassis. This terminal is soldered directly to the chassis. So we have a direct chassis ground on our common, and that goes to our common leads to our speaker terminals. We moved our feedback loop tap for our global negative feedback. We moved that from the 16 ohm to the 8 ohm, and then we adjusted this value a little bit from it was like a 6K resistor to a 4.3K resistor. Okay, and we pretty much kept this the same. I put 120 picofarad. So if you look here, here's our feedback resistors. Okay, and believe it or not, these look pretty small, but these are actually 1 watt resistors. A lot of these newer resistors are a lot physically smaller than the old ones. This is not carbon comp, and we'll talk about resistors here in a minute. The other thing we did, so pretty much our gain is going to be the same as it was. We haven't really changed that. We just modified some things to make it more quiet and to make this thing more linear at 8 ohms, because most of the speakers we're going to use are 8 ohm impedance speakers, so we want our feedback tap to be there. The other thing is we changed a couple of values here on our bypass capacitors and our cathode resistors. So we went from 100 ohm to 150, and we went from a 25 microfarad to a 470 microfarad. And we changed the feedback tap from this split off point, and we moved it up here directly onto the cathode itself. So that's a big change. This wire here is gone. This whole wire here, I completely removed that. That has to do with a balance check circuit that was in. I removed all that. I don't want any noise. I don't want signals going back and forth to the front panel and to a bunch of noisy switch contacts. I got rid of as much of that as I could. The other thing I got rid of was the speaker phase. You can see this here. I removed all that. So now we have the signals coming directly out of the transformer and right into the speaker taps. Okay, so that's what we have now. Another thing we added, and this was in addition, another pot to tweak, we added a 10K resistor into our driver section. And what we call this is an AC balance. Okay, so first of all we have our bias balance. Don't get the two confused. So we have our bias pots down here. These set the bias voltage for our output tubes. This sets our idling current of the tubes. Okay, with this bias pot. This is an adjustment to compensate for any differences between our tubes. So let's say these tubes aren't perfectly matched and they have slightly different gain characteristics to one another, as tubes often do. This balance pot will allow you to offset your bias between the two tubes so that they each are equally biased to the same idle current. Okay, this does a similar thing with your driver stage. This is a single tube here, a 6SN7, so it's 2 triodes in one package. And the purpose of this is if these 2 tubes inside the one package are a little bit different from one another, this allows us to balance them so that they both are working exactly at the center of their operating point. So we're going to put an AC signal through it, and what should be coming out of it is an equal AC signal that's basically symmetrical above and below the center line, the ground, the 0 volt line. And that's what this does. So if you notice, one resistor is a little bigger than the other, 27K and 22K, and then this 10K is in the middle, and the whole idea is I can shift this pot. So this is 27 and 27 or whatever. I can make these equal amount, or I can offset them one way or the other depending on the tube. And that's what this is for. Again, it's hair splitting, really, because these are usually pretty balanced, but this allows you to get it perfectly centered. So where you really notice it is when you're at very high volumes or very low volumes. You'll notice more clarity in the sound because this is operating perfectly in its center of its operating region. So that's what that is. The other thing we did was these we reduced a little bit. So we went from a 0.1 microfarad to a 0.047. The reason for that is we wanted to cut a little of the energy that's getting to these grids. One thing you'll see on these older tube amplifiers, some of them, is they tend to have what I don't know what anybody else calls it, but I call speaker flutter. Because of the output transformer, tube amplifiers do not usually have a high damping factor. In other words, they don't have the ability to dampen out a speaker when it's working. And I guess the best way to explain that is if you take a loose speaker in free air, like a woofer that has a real, high travel or high excursion as we call it, if you tap that speaker, it'll have kind of a warbly low tone to it. But if you take the two speaker leads and you short them together with a jumper lead and you tap it again, the frequency will be higher and the speaker will have more of a thud to it instead of a ring. It's because that speaker is being dampened. In other words, the energy that's created by that moving coil on the magnet, okay, is actually working against itself because it's shorted. And a transistor, being a very low impedance device, helps that to happen. So it makes the speaker not flutter around so much when it gets moving. It makes, when people talk about the bass is very nice and tight sounding versus a loose sounding bass, that's what they're talking about. And the more energy you put into these, the lower or the higher the capacitance you put in here, the more at low frequencies, like at the rumble below hearing range, subsonic frequencies, you're going to pass into these grids. They're going to pass right through this transformer, and it's going to contribute to that loose sounding bass. So we're tightening that up a little bit by decreasing the capacitance here. It's still going to allow all the audible frequency range to pass through here from 20 hertz to 20 kilohertz. It's just going to help limit a little bit the speaker flutter. So that will hopefully clean that up. So these little improvements here that we made, all in all, should contribute to a much better sounding amplifier. Now, I'm not using ultralinear taps on the, because this is strictly a non-ultralinear amplifier. I'm not using any kind of fancy transformers. So this is going to have a very classic warm tube sound, but it's still going to be a good sound. It's not, hopefully should sound good and not sound all, full of hum and hiss and, the bad things we don't like about tube amps, but still retain all of the charm and all of the good things that we like about tube amps. So that's where we are right now. I do have a new set of 100 ohm hum balance pots that I may replace. I don't know after I listen to this a little bit. But this thing's ready for its first power up. So I'm going to get it turned around and I'm going to get it turned on. I'm going to get all the controls set to kind of a default setting point. And then we're going to try to walk through this. First of all, make sure all the wiring is good. Make sure it powers up. And then see if we can get the tubes to bias properly and to balance. And see if we can get some sound pushed through here. So once I get those things set up, I will be back. So thank you for listening to the long-winded speech. And I'm sure it wasn't perfect. And I'm sure there's other people that could explain things a lot better than I did. But that's my nickel tour, the best I can give you. So, all right, stay tuned and we'll be right back. Okay, we have a little bit of an angled shot here that we're doing, and I'm going to try to move things close enough together so that we can actually see everything in one shot. I'm not sure if I'll get it all in here or not, but we'll try. Let's drop the camera a little bit. Kind of get in there. Now, I don't know if you're going to be able to see all of this, but we'll give it our best shot, huh? All right. So, okay. All right. So what we have, move this over, is two test points, one for each vacuum tube on each side for the outputs. Okay, so we have one here, one here, one here, and one here. And the first thing we really want to do before we do anything else, and I hope you can see this, I really can't see on the monitor here, but what we want to do is we want to bring the power up on this and see what kind of bias voltage we have. These are your bias test points. And basically what they're looking for is approximately 380 millivolts on this, on each socket. And really all we're doing is we're looking at one tube for each channel with my 2 meters. Okay, so the first thing we're going to do is turn this on and let it warm up. So here we go. So here's power. So we have the machine turned on. And basically there is no input signal right now. We have the whole thing shut down. I have volume all the way down. And we're just waiting for this to warm up. And as you can see, it's climbing. So this channel here, so this meter represents the left channel, this meter represents the right channel. And if you look right now, they're coming up. This side here is sitting at 360 millivolts, and this side here is idling at about 330 or 325 millivolts. So what we're going to do is we're going to come in here and we're going to adjust it after it's been warmed up for a little bit till it sits at about 380 millivolts. Now, the way to adjust the bias is going to be these two pots here, this one here and this one here. These two actually set your bias level. And all you're doing is you're applying, if we look here what we're doing, let's get some schematic in here. So you have these two pots here. They're coming off of a negative power supply. See, the diode is in backwards. So we have a negative, and the capacitor is grounded with the positive lead. And we basically have two negative voltage supplies, one here and one here, connected to two pots. And that's these two pots here and here. Okay? They go up to points R and N, which are, there is N and there is R. They go into the balance pots. Okay, so we got the balance pots kind of set in the middle, roughly. And so we know if these tubes are matched, it'll be ballpark close. So what we're going to do is we're measuring J19, J21, J20, and J18, if you look there. So really what we're doing is we're measuring with respect to ground here. You see, from here to here, we're measuring the voltage drop across that 10 ohm resistor. So if we have 10 ohms and we use Ohm's law, okay, and we have 380 millivolts, okay, I equals E over R. So let's work that out. Okay, so I equals 0.38 okay, divided by 10 ohms equals 38 milliamps. So basically what we're looking for is an idling current through these tubes of 38 milliamps each. Now, by applying a negative bias voltage to your grids, you can see that splits through these resistors here and goes to the grids. That negative bias voltage is going to adjust the idling current of each tube. So we're going to set them for 38 milliamps, which is 380 millivolts. Okay, so this has been sitting here for a few minutes, and what we're going to do is I'm going to shut the camera off for about 5 more minutes or so, let this thing warm up and stabilize, and then we're going to come back and I'll adjust those and you'll see what happens. Okay, so sit tight and we'll be right back. Okay, we're back, and the amp's nice and toasty. Tubes are nice and warm, and now we're going to go ahead and adjust it, and you can see these have kind of stabilized out. So just so you can see right here, let me go down, I'm going to be adjusting this pot and this pot. Okay, so this one here is going to be the right channel and this one here is the left channel, and what I'm going to do is I'm going to zoom you in on the meter so you can see as we adjust it how it reacts. Okay, so here we go. Alright, so let's start with the left channel, and that's going to be this meter right here, and I'm going to adjust it just ever so slightly and then let it stabilize. Okay, we're just going to let it sit. You can see how it moved just by tweaking it just a little bit. And to be honest, what I like to do is, if anything, I like to make it a couple of milliamps lower than what they recommend, because as the amp performs and gets hot and seasons, that'll creep up a little bit. And you can see it's creeping already a little bit. See how it jumps around? Alright, now we're going to adjust the other channel, which is the other pot, and that's going to be this meter. Okay, went too far, see that? I'm barely touching this pot. Okay. And you can see when I adjust one channel, the other channel is affected by it. And the reason is, if you noticed, both of those pots are connected in parallel to that power supply. So they're putting a little, by adjusting this, you're putting a different load across there, and it's causing one channel to affect the other. So this is kind of a little balancing act. And remember, we're not done. Once we do this, we have to balance the two tubes. We just know that the two individual tubes, on one tube on each channel, is idling at the correct current. But now what we want to do is make them idle at the same current and then go back and readjust it again. Okay? So I'm pretty happy with where that's sitting right now. You can see it's right around 360, 370, 375. It kind of floats around a little, and that'll be okay. So now I'm going to show you what I'm going to do. I'm going to take my ground leads. Okay, so these are tied to ground right now. These jumper clips are just connected to the chassis, and I'm going to move this over here, and I'm going to now put my meter across those two resistors, you see, between the two tubes. What this is going to do is any difference between the two tubes is going to show up. You see that? The one side is actually out of balance by quite a bit. This side's not too bad. This side is out a little bit. So if you look here, see that balance pot run right there, and another one right there? We're going to adjust those until these come as close to 0 volts as we can get. And what you're going to find out is, as I'm adjusting this, you're going to see that this these are extremely touchy. You just barely move them. See that? Literally just putting the tweaker on the pot moves it. So we're just going to go a little bit at a time. And it takes time to settle, and you can see it swung from negative to positive here, so one tube being higher current to the other tube being higher current. But that's really good there. This other one, we're going to adjust it, and you can see we're just barely going to touch it once again. Going the wrong way here. There we go. And you can see this channel is really quiet. Both of these tubes are very quiet. This tube here, one of the tubes is a little bit noisy. And remember, this meter actually has 3 positions past the decimal point. This one only shows you 1. So kind of disregard these last 2 digits. And you can see it's just kind of bouncing around. But you're only talking about 1 millivolt difference, which is beautiful. So these tubes are perfectly balanced now. Okay? Now that we've done that, we want to actually go back and we want to look at those first 2 pots again, and we want to look at the actual idle current. So we take our ground leads and we connect them back to chassis ground, just like we had. Okay? By the way, guys, this is pretty much any tube amp that has fixed bias is going. This is the same procedure. The only difference is the voltage level that you bias it to. Every amp is different. So this one's 380 millivolts. Another amp may be 200 millivolts or 60 millivolts or whatever, depending on what dropping resistor you're reading across and the tube. The 7591 tubes are happy at that, and actually this amp runs these tubes a little bit too hot, in my opinion. And if you notice, this one's a little bit high now, so we have to bring it back down. Okay, because the one tube was a little bit higher than it. So we're going to just bring this right back down, and now we can get it closer to 380. Okay. Okay, and there they are. Okay, so now that's really good. Now you want to just kind of let it sit for a while to give it some time to see if the tubes are going to drift a little bit over time. Tubes with temperature will drift as all the components inside the amplifier heat up, the resistors heat up, and so forth. You get little variations, but nothing terrible. It'll sit right around there. Okay, now that that's done, okay, the next thing we have to do is we have to check the AC balance. Now these are the new pots that we installed. This is something that you don't see in most amplifiers, and this was a modification we made to the circuit. Okay, so let's zoom you out of here while this thing sits, and I'm going to show you something here in the schematic again. So once again, we have this balance pot up here, and what it's doing is it's adjusting, basically it's adjusting your idle voltage or your voltage between the 2 parts of the 6SN7 tube, these 2 triodes. And the idea is when we put an equal signal on both grids, we want to have an equal signal coming out and going into the final tubes, into the output tubes. And what that AC balance pot allows us to do is to adjust that. Now, good quality tubes are usually pretty well balanced from one to the other, but not always. So this will actually make the amp even more accurate. Now, there's 2 ways that we can do this. And just so you know, since I had this up on its side, I already adjusted these pots. But the way I prefer to do it is I pull the output tubes out, get them out of the sockets, and then I turn the amp on its side, or flip it upside down, power it up, and then I put my oscilloscope between this tube right here, right after the decoupling cap, and right here after the decoupling cap. Okay, and remember, this amp, you want to make sure it's plugged into an isolation transformer just for good measure, because you never want your scope to be to get any kind of ground loops or anything and just damage your equipment. So we test here and here, and you should see two sine waves, and they're each 180 degrees out of phase. And what you're going to do is you're going to adjust those sine waves until they're both totally 100% equal to one another. Okay. The other way you could do it is if you have a distortion meter, you can connect it up to your speakers and do it that way. But really, all you're trying to do is you're trying to get a symmetrical waveform through your output tubes. So now that the tubes are properly balanced, we want to balance our driver stage with this. And if everything's properly balanced, when you see clipping in the amplifier, it should clip exactly the same amount on the top and the bottom. If it doesn't, then something's a little bit out of adjustment. The other thing that can do is that can make up for some of the anomalies in your driver tube here, or your preamp tube, your line stage tube. So if it's a little bit out of balance, this will correct for that as well. Okay. Once you do that, you can actually put a signal from your audio generator into there, and if all goes well, which we know that it doesn't always, we should be able to see something come through here now. Well, let's see what we've got. Oh, it would help to turn the signal generator on, huh? Okay. Alright. So I'm going to start out with a 1.2 volt RMS sine wave going into the auxiliary input of the amp at 1 kilohertz. And let's turn this on and turn it up and see what happens. So you can see right here. Alright, do you notice something? Okay, and you can see how it's perfectly clipping on the top and bottom. Okay, and you can see your little bit of crossover distortion there as the amp starts to clip. If we come below clipping, we're good. But if you notice here, I don't know if you guys can see that on the camera, but what we're getting is, you can really see it there, you're getting a little bit of oscillation, a little bit of ringing from your output transformer. And that's through the feedback circuit. Okay, now let's go back down to the table here and I'll show you what I'm talking about. So right here you have your global negative feedback. Comes across here and down here. And if you notice, across this resistor we have a 120 picofarad capacitor. See that? And it's shunted across that 4.3K resistor. And if that capacitor sometimes has to be adjusted, because sometimes you'll get that little bit of oscillation, that little ringing there. That will actually get rid of it if you get the proper value in there. So you may have to go up, you may have to go down a little bit. Okay? And again, what works for me may not work for you. You may have to adjust that just a little bit. It is a finicky little adjustment to make. But if you get that ringing, you have to adjust this capacitor here until you get a nice clean sine wave coming out. And it's even better if you can use sometimes. Let's see what we get now. Try to put a square wave and see what that looks like. Sometimes the square wave will show the oscillation much better than a sine wave. So let's see what that looks like. Now on some tube amps, they don't like square waves at all. But we'll see what this one can do. I've never tested this one. Let's see what we get. Oh my goodness, look at that. We have a really unhappy square wave there. And again, that's part of the amplifier. Now, strangely enough, if this were a Macintosh amplifier and we were using a unity wound output transformer, that circuit that they use, the square wave would be pretty nice. It would look pretty good. But as you can see on this one, it's not doing so well with that square wave. So now one of the things that I'm going to do is I'm going to experiment a little bit with that capacitor and try to get that to look cleaner. And then I'm also going to go in there and I'm going to try to go back in the circuit and see if the square wave looks good going into the output section. Okay, we can check that. Again, we would look at that in the same place that we would look at the AC balance adjustment. And that would be, once again, right here and here. Chances are that square wave may be a perfect or almost perfect square wave right here. If it's not, I'd go back to here and look. You know, go work my way back until I see a good square wave, and then I know what section that I'm getting that distortion. I have a feeling when we check it, it'll be good here and bad here, and that'll be a function of the feedback and a function of the transformer itself, because again, the permeability of these transformers, that's the difference between a really super expensive high-end transformer and a lower end. Rumor has it these are supposed to be excellent transformers, so we're going to find out. And this is the fussy part of restoring one of these amplifiers. Okay, I know I'm taking up a lot of your all time looking at this, but these are the things behind the scenes you have to do to get these things to work at their best. Okay, so don't get me wrong. If I plug this into a set of speakers right now and put on a song, it would sound okay. It would sound pretty good, but nowhere near it would not sound like what it could if you have everything properly adjusted. Okay, so let's go in and try to get rid of that ringing and try to get the square wave to look better, and I'll be back. Okay, problem solved. Let's look at our square wave again at the output. You can see pretty darn nice. What do you think? Getting a nice solid signal, nice looking square wave. You can see I can get up pretty loud. Okay, and what did I do? Well, I looked at my tone controls and noticed that bass and treble were not set flat. Now, by turning the bass and treble up, all of the components in the bass and treble controls influence that square wave and cause it to distort like that. So, two things that tells me. Number one, that, you know, the tone control influences the circuit. But number two, chances are that's the one part of the amp that I have not done yet. I've not refurbished or restored or changed or modified. And it's using those little couplets or couplets, whatever you want to call them. And those couplets are actually, let's see if we can look at them right here. If you look, they're right down here. See them? Right here. And wherever you see that dotted line, all those little components are inside there. Again, they are ceramic type capacitors and so forth, and most likely they're not working too good. So what we're going to do is, if you recall in the first video, I made up these new tone stacks, and we're going to fit those in before we're done. But with all the settings set flat, everything is working very well. Now we're going to go back and let's check our sine wave once again. Okay, and let me get you back up on the scope. I haven't checked this yet, but I bet you, I'm really interested in seeing if that ringing comes back or not. So let's check that now. And look at that. The ringing is all gone. And you can see it's perfectly breaking up symmetrically. See how perfectly balanced that is? And we're getting about 26 watts per channel, which is more reasonable for what I'm thinking one of these amps should put out. A 7591, to push them to 35 watts per channel is really kind of, you're asking for too much. I just think that's a little too much to ask. So so far so good. Now let's try a couple other things. Let's go drop our frequency, and I'm going to go down to about 35 hertz right now, and let's move this sweep time down a little bit, and let's see what 35 hertz looks like. As you can see, you're seeing some things here that aren't looking like they should. Okay, and that's in the output section. So once again, I'm not getting a symmetrical output, and that's again is the tone control, I believe, influencing it. Because you can see if I turn that pot, I turn the bass up, one side adjusts more than the other. See that? As a matter of fact, that one, the bass pot isn't even working on that one channel. See it? So there we go. So yeah. So those tone control pots have to go. That tells me they've drifted and they need replaced. But when we have them set properly, you can see I have a really nice, pretty nice looking 35 hertz there. Okay, and if I take you here off the stand for a minute and I put you down here on the, this is actually the preamp section, driving, coming out of the preamp, the line stage. You can see how clear that is, alright, as I turn it up and down. So far so good. This amp is performing very well, but we still have problems in our tone control section, and that's what we're going to address next. But I am now convinced that the output section and the driver section are properly adjusted, and sorry about that terrible view I'm giving you. Everything's properly adjusted, and I think we're ready to move on to some of the finer things in here, like the tone control and the phono stage. So that's where we're going to go next. Alright, so I got the amp turned back around, and I'm going to get ready to look at all this mess down here with all these disc capacitors, all these dirty switches. I mean, I cleaned them and everything, but it doesn't matter. These pots and the tone control. This video is getting rather long, so I think I'm going to end this part here. I'm going to upload this one, and when we come back on the next part, we're going to be working on the front end of this amp, the tone control and the switches and all that sort of stuff, and we're going to try to fine-tune this and get the best we can out of it. So that ends this part. I really hope you enjoyed following along with me on this, and more to come.